All right, so today we'll finish up 4.2. So as I said, we're going to look at problems that have asymptotes that are still vertical. That's not going to change. Still going to have those. It's not going to change how you find them either. What's going to be different is we might not have horizontal. So yesterday, this is what we did. We graphed functions where the degree in the numerator was either less than or equal to the degree in the denominator. Okay, so that's just what we did yesterday. Today, we're going to graph functions where the degree in the numerator is larger than the degree in the denominator. And really, what the important thing is how much larger is it, right? Like if you have x cubed in the top and you have x in the bottom, that's not too bad, right? Because they're only cubed in the top, first power in the bottom. That's a difference of 2. The more different they are, the more complicated the asymptote gets. So I already told you, for the problems we do, they're only going to differ by 2. So maybe you'd have x to the 5th in the top, x cubed in the bottom. 5 minus 3 is a difference of 2. Okay, and when we do that, we're also going to get something a little different. We're going to get what's called an end behavior asymptote. So we've done end behavior model. That's easy to find. Okay? We're going to now look at what's called the end behavior asymptote. So first, this assumes that you're dealing with rational functions, which is what this whole chapter is about. So you've got two polynomials, h of x and g of x, and you're going to divide them. Well, you already know how to find the end behavior asymptote. I taught you that last week. I didn't call it an end behavior asymptote. I called it long division, or synthetic division. Well, that's what you have to do here. Okay, to find the end behavior asymptote, you would do division. Okay, when you divide, you're going to get a quotient, you're going to get a remainder. Okay, sometimes the remainder might be 0, that doesn't really matter. What we're focused on this time is just the quotient. If you can do long division and find the quotient is your end behavior asymptote. Right. And what I've done here is I've written it out the way you would check your answer with long division. Quotient plus remainder over divisor. Well, think about if your remainder was a number like 2, and your original divisor was, let's pretend g of x was x plus 6. Well, this part, I don't want to circle it because it's not important, but this part doesn't matter because think about what would happen as x gets bigger and bigger. Let's pretend x is 1,000,000. If x was 1,000,000, the part I just circled would become 2 divided by 1,000,006. That's a very small number. And the bigger x gets, the even less significant that circled part becomes. All right. So that's why that part doesn't really matter. It's the quotient. And that's your end behavior asymptote, which from this point forward, I'll just call it EBA. So the EBA is a little more work to get than the EBM. EBM is easy. You just divide the biggest term and the highest degree term in the top by the highest degree in the bottom. That's end behavior model. End behavior asymptote, you got to do long division. Or you could do synthetic, if it applies. But I think most of the time we're going to have to do long division. Okay, any question on that? So this end behavior asymptote is going to predict what's happening to your function as you head very far left and right, like towards infinity and towards negative infinity. And it'll never be horizontal. Okay? Best case scenario, it's going to be slanted, the line slanted. Worst case is it starts to curve. All right, so let's try this one. For now, we don't even have to sketch it. We're going to, but they just want us to find the quotient the remainder, and the end behavior asymptote. Does anyone have a guess what degree the end behavior asymptote is going to be? Before we do out our division. Yep.
Squared.
Squared, yep. It's going to be a degree 2. This is going to be a parabolic asymptote. So let's do out, it doesn't matter. In this case, you could do long or synthetic. I'll do long division because I'm not going to guarantee you always have a problem you can use synthetic on. Right? But long division, you can always use it. So x minus 2 into 2x cubed minus 4x squared plus 0x, don't forget that, plus 3. Okay, so let's divide it in. So Kaya, if I take 2x cubed divided by x, what do I get?
2x squared.
Yep. 2x squared. Multiply it back out. 2x cubed minus 4x squared. That's actually going to be pretty nice. And now subtract. Gabe, what's 2x cubed minus 2x cubed? 0. And Emily, negative 4x squared minus negative 4x squared. It's also 0. Now bring down the next term, which is 0x. And, I mean, we're pretty much done at this point, because if you try to take 0x and divide x into 0, you get 0. So you get 2x squared plus 0. If you wanted to keep going and see what the remainder is, I mean, you could, but the remainder is not important. I have my end behavior asymptote right there. All right. But just to show you how it would finish up, 0 times x is 0x. 0 times negative 2 is 0. I have to bring down my 3 so I have something to subtract it with. Subtract 0 minus 0 is 0. 3 minus 0 is 3, so the remainder is 3. Again, I don't care about the remainder at all. All right, so now let's just write down nicely what they wanted. The quotient. What's the quotient here? Yeah.
2x squared.
2x squared. The remainder. So, I guess I said we don't care about the remainder. I mean, the problem wanted to know it, but in terms of what's really important in this problem, it's the quotient. That's what we need to do our graph. Chris, what's my remainder? 3. So I got a remainder of 3. We're not going to use it for anything other than what I just wrote right there. And now the end behavior asymptote. Kathleen, what's my end behavior asymptote?
2x squared.
Yeah, it's the same as the quotient. Right, so that's everything they wanted to know. Any questions on that? So now, remember, another way you could write this answer, if you didn't want to write quotient and remainder separate, okay, you could say your answer is quotient plus remainder over divisor, x minus 2. And now I want you to look at that, and as x gets bigger and bigger, right, as the absolute value of x gets really big, so whether it's a really big negative number, a really big positive number, what happens to the remainder part as x gets bigger and bigger? What does that fraction get closer to? Yeah.
Closer to 0.
Gets closer to 0. Right? If x was 1,000, you'd have 3 divided by 998. Very small number. Right? So that's why the part that I circled doesn't even matter when we're talking about end behavior asymptote, because it gets very close to 0. So what happens to the remainder as x approaches infinity? The remainder approaches 0. Okay, that remainder part gets closer and closer to 0. All right, so three kind of important things to keep in mind. There's a difference between the EBM and the EBA. EBM, I already mentioned, divide the highest degree term in the top by the highest degree term in the bottom. EBA, you do long or synthetic division. So they're different. The process to find them. But once you find them, sometimes the EBM and the EBA are the same. They could be. In the last problem we just did, they would be. The end behavior model and the end behavior asymptote would be the same. The reason they came out the same in that last one is because something special happened. When we did our long division, two things canceled at the same time. If that hadn't been a negative 4x squared right here, I would have had an x term up in the top. And then my EBA would have been like 2x squared plus x. Okay, I would have had some kind of x term. Still would have had a remainder, which wouldn't have mattered. But I might have gotten an x term, and I might even have gotten a constant. So it might have been like 2x squared plus 3x plus 6. Okay? But because of that double canceling that happened, and the fact that this term was also a 0, a lot of things lined up just right to make it so the long division comes out exactly the same as the end behavior model. So that doesn't always happen. Okay, and kind of comparing it to what we did yesterday. If the degree of the numerator is less than or equal to the degree of the denominator, you will always have straight line asymptotes. Always. If the degree of the numerator is less than the degree of the denominator, asymptotes are straight lines. If not, the asymptotes can actually curve. Okay, so the problem that we're going to graph, which is the last one we just did, that's going to have an end behavior asymptote of 2x squared. That's a parabola. So we're gonna try to sketch that. So any questions on the difference between the EBA, the EBM, or when you have straight asymptotes and when you don't? Okay. So now let's verify that 2x squared really is the end behavior asymptote. Okay. The way I'm going to do that is I'm going to graph the original problem. I'm going to graph 2x squared, and I'm going to see if it looks like my original graph is getting closer and closer and closer to the EBA. Right? So I need the original problem. So we've got 2x cubed minus 4x squared plus 3 divided by x minus 2. So I'm going to do that in blue, and I'm going to put the asymptote in red, 2x squared, and I'm also going to make it a dotted line. So I can make it dotted just by going over to where I can change the color, hit enter, and then I'm going to go down to the line and just find the one that's dotted, and then go to OK. You don't have to make it dotted, but if you want to draw it the way we've been doing it, it should be dotted. Okay, so let's look at it. And I might have to zoom out a little. I think I'm going to have to. Yeah, let's zoom out. Well, you can kind of see from here. See how the graph in blue and the dotted line in red? Everyone see how they're getting closer and closer together? So that curve in blue is following a parabolic asymptote. That's the asymptote. Now, there's another part to this graph. Whenever you have a parabolic asymptote, it should come back in on the right side somewhere, usually kind of, well, I'll sketch it and show you, but it should come back in up there somewhere. So let's set the Y max higher so we can see it. Let's try, I'll just try 25. Right, so there's the left part. We already had that. There it is. And there's the right part. Right? It's still a little hard to see because I didn't go super high, but you can start to see that the asymptote in red and the graph in blue, they're getting closer and closer together. And as you head to the right, eventually the dotted line in red and blue, they're going to be right on top of each other. And they basically look like they are there. So, right, so that's what we're going to try to sketch by hand. Right, so any questions on how we just verified that 2x squared is the end behavior asymptote? Just make sure it's getting closer and closer to it. That's all I do. All right, so now let's try to sketch it. This is a little different because we already graphed it, so we already know what it looks like, which kind of helps us. But let's go through it like we didn't know. What's one type of asymptote that we should always try to find first? And this is an easy asymptote to find. Yeah. Yeah, you should always find your verticals. And in this case, it's this, in every case, it's the 0 of the denominator, as long as you don't have a common factor, and here we don't. And it's x equals 2. So let's put a vertical line in at 2. All right, so I'm going to get closer and closer to that line. And now, the next thing we would want to do is we would say, okay, degree in the top is bigger than the degree in the bottom. 3 versus 1. Do long division and get the end behavior asymptote. We already did that. So end behavior asymptote is 2x squared. So now I want to draw 2x squared, okay, as an asymptote. So the way I'm going to do it is just plot some points. If x is 0, think of it this way. If x is 0, what would y be? Yeah, 0. What about if x was 1? Y would be 2. So if x is 1, y is 2. If x is negative 1, y is also 2. What about if x is 2? Eight. And it's symmetrical. So if it's 2, we're at, oh, did I go a little high there? 1 and 1. Because my graph goes by 2s. So if x is 2, we're at 8. Negative 2 is also 8. And then can I fit 3 on there? 3 squared is 9 times 2 is 18. Yep. So 3, 18, and negative 18. So I get a parabola. I'm going to sketch it, and then I'm going to change it to a dotted line. So let's try to do the best I can with it. And I'll make it dotted because that's an asymptote. So what we're really going to be focusing on is something's going to be happening in here. That's where part of my picture is going to be. The other part of my picture is going to be over here. Okay? Those are the two parts to my picture. So now we got to plot some points. Let's try. I think I already have it typed in. Don't worry about y2. That's just the asymptote. Focus on y1. All right. Well, we know if we type in 2, that should be an error. Let's try it. Yeah, it is. That's my vertical asymptote. Let's try something very close to 2. Let's try 1.999. I'm at almost negative 3,000. So just before 2, way down there. Let's go just after 2. Positive 3,000. So just after 2, I'm way up there. I want to get some more points, okay, because I'm still not 100% sure what the graph is going to look like. So I'm going to try 1. When x is 1, I'm at -1. Oops. Keep forgetting my graph goes by 2 on the y-axis. So I'm going to go right through that point. Let's do 0. 0, -1.5. So right about there. All right, let's try -1. -1, 1. So -1, 1. So I'm going to be right about there. So I'm starting to get an idea of, if we go back and look at the graph, we can kind of see this curved part happening here. It's going to come up, stay pretty close to that, but then at some point it's got to start curving because it's going to go through these dots. So it's going to curve through them, but it doesn't keep going down because then it curves back up and goes through that dot. All right, so it goes like that. And then I think from here, all we have to remember is it's just going to kind of hug that parabola and stay very, very close to it. All right, so now we just try to sketch that the best we can. Getting closer, closer and closer. That's as good as I can do it. Okay, so that's the left part. Now, whenever you have a parabolic asymptote, it's going to come back in somewhere else. And it's always in that section right there. Okay. So now what I want to kind of figure out is some different values in here. So I did 2.01. Let's go 2.1. Just a little bit further past 2. It's coming down very fast. 2.3, right? It's down at 20. 2.5, it's at 18.5. So that's probably a good one because I can fit it on the graph. 2.5, just a little above 18. And now let's try 3. Now it's going back up again. So at 3, I'm at 21, which is right about there. So now I've got 4 dots that I'm going to be going through. Let's make it a little bigger. So as I head this way, I get closer and closer to that green asymptote. And then as I head to the right, I'm not allowed to cross the dotted line. So think of that black, bless you, that black dotted line. It's like a boundary. You're going to hit it, and then you're kind of forced to curve up, getting closer and closer and closer to the dotted line. And if we look at our graph, that's pretty much what it looks like. All right, so any questions on that one? So that's the trickiest one that we sketched today. We're okay with that one? It's really just plotting a lot of points because that's the only way to figure out what it's going to look like. And I did a lot. I did like 10 or so points. Okay, so you got to just do a lot of points. Always check points near the vertical asymptote. So, just to the left, just to the right of it. And then if you ever come across a parabolic problem again, you know what it's going to look like. It always looks something like this, and then it has another little section right there. They all pretty much look like that for the parabolic ones. The curve might be a little different. Might be a wider parabola, but that's the basic look. All right, let's look at this one. So it says determine the end behavior asymptote and then sketch a graph. What degree do you think my end behavior asymptote is going to be this time? degree 1, why do you say that?
Because x cubed minus x2.
Yeah, so we have a degree 3 in the top, a degree 2 in the bottom. That's a difference of 1. This is not as bad as the last one. Degree 1, that's linear. It's not horizontal. But it is going to be a line. All right. So let's start like we always do. We'll start off with the vertical asymptotes. What would I have to do there to make the vertical asymptotes easier to figure out? Yeah?
Factor.
Factor the top or the bottom?
Bottom.
Bottom. Yep. So 2x cubed plus 7x squared minus 4. Now the factoring doesn't really help you for anything else. The only reason to factor it is just to get the vertical asymptotes. Okay, and how does that one factor? Blake?
X plus 3 and x minus 1.
All right, let's try it. X plus 3, x minus 1. We get x squared minus x plus 3 is plus 2. 3 times negative 1. Yep, looks good. So Blake, what are my vertical asymptotes?
It would be negative 3 and positive 1.
Yep. So there's your vertical asymptotes. So let's put those in. Negative 3, positive 1. Let's see. Are we going to have an end behavior model that we need to find for this one? Did they ask for it? No. How about the end behavior asymptote? Is this a problem where that applies? Yeah, because the degree in the top is bigger than the bottom. Could you do synthetic division here? What do you think? When can you use synthetic division? Remember what the bottom has to look like? Give you a hint, it's not that. So that is not something you can use synthetic division on. But how would you know when you can? Because if you can, it's a lot faster. Yeah.
Is it x minus c?
Yeah, it has to be x minus c, x minus a number, right? If it's x plus a number, that's okay too. You can think of it as x minus a negative. It's the same idea. But it's got to just be an x, a plus or minus, and a number. That's not what you have there. So you've got to do long division. So let's, I need a little more space. So x squared plus 7x squared, or actually x cubed, sorry. Plus 7x squared minus 4. Okay, that's going to be my, what I'm dividing into. And then x squared plus 2x minus 3 on the outside. Oh yeah, there's one other thing I need to do. That if I don't, it's going to be a problem. Not right away, but it will be. What didn't I do?
You didn't add the 0x.
Yeah, I want to put in the 0x. Yep, that's important. Okay, so let's divide it out. 2x cubed divided by x squared. How about, Ashley, what does that give me?
2x.
Let's see, yep. So 2x, multiply it back out. 2x cubed plus 4x squared minus 6x. And subtract all that. 2x cubed minus 2x cubed, that's gone. And Joe, what about 7x squared minus 4x squared?
It subtracts it by x squared.
3x squared. And then 0x minus 6x. That gives me plus 6x. Okay. Any question on the first stuff? Yeah.
Why'd you write plus?
Oh, take minus 4. And then bring down your minus 4. Okay, everything else looks good. And now the next step is the last one. Okay, because all I'm interested in here is the quotient. I don't care about the remainder. So let's divide x squared into 3x squared. And what do you get? Yeah, just plus 3. That's it. So at this point, unless you want the remainder, you can stop. So your end behavior asymptote is 2x plus 3. So we got those. Behavior asymptote, 2x plus 3. Not as bad as the first asymptote we did. Not as nice as a horizontal, but what is that? 2x plus 3. It's going to be a... What kind of asymptote? Yeah?
A line.
It's a line. What kind of line? Can you describe it a little more specific?
It would have a slope of 2
Mm-hmm.
and cross the y-axis at 3.
Yeah, it's going to be a line with a slope of 2, and it's going to cross the y-axis at 3. So I'll put a dot on 3, put a few points for my line, and now I'll put in a line that looks like this. So, kind of like the problem we did yesterday, we've got the different sections, except it's not a horizontal. It's on kind of an angle. Okay. Any question on that one? And now we're just going to use the table and try to get some points. So I'll check on each side of -3 and 1, and I think that'll be enough. If we need more points, we can plot a few more. Okay. Plot as many as you need until you get a good graph. So 2x cubed plus 7x squared. Let's do it like this. Plus 7x squared minus 4 divided by x squared plus 2x minus 3. I like to check the asymptotes just to make sure I got those right. So let's plug in -3, okay, as we expected, and 1. That's also what we expected. Okay. What's a value just to the left of -3? Yep, kind of.
-2.99.
Okay, we can do that one.
Or
It's not to the left, but that is one I want to do eventually. So -2.99, we're over -1200. So that would put me way down here. What would be another good value to plug in? Yeah, -3 I would go even closer.
3.001.
Sure, that works. We're up over 1,000. Okay, so that's going to be up here. Okay, so far so good. What's another good number I should check? Yeah, Chris?
0.9.
0.99. Yep, I like that one. We're at -1,000. So way down here. And what's one more good one I can check with the involving the asymptotes? Yep.
1.001.
Yep. And just after 1, I'm way up over 1,000. So I'm up here. All right, so I'm going to have 3 sections to this graph. All right. Each section is going to be trapped by those dotted lines. It cannot cross, can never cross them. So let's start with the section on the left. Let's do -4. Okay, let's get another point on this graph. -4, -4. Okay. So 1, 2, 3, 4. 1, 2, 3. Right there. I think that's enough for me to get the left graph. I have to stay very, very close to that asymptote for now. But then, as I start heading to the bottom, I run into that asymptote that's on an angle. So I can't cross it. The only thing I can do is I can try to get close to it like that. So that's the left-hand section. All right, let's look at the middle section. I know I have to stay very close to the asymptote here and very close here. I've got those 2 points. But what's happening in the middle? Let's get a couple more points. So let's get 0. The point 0, 1.3 is on the graph. So right there. Let's do -1. -1, -1/4. So right about there. And I think that's enough. So what's going to happen is it's going to come up, slowly going away from the asymptote a little bit, but it can't keep going straight up because it runs into another asymptote. So it's going to hug it, go right along it. And it comes up, starts to curve, and it says, okay, I just want to keep going this way. But it can't. It runs into another asymptote. So if it wants to, it's got to stay very close to it. So at some point, it's going to turn and then get closer and closer and closer to that asymptote. Right? So by having those 4 points, that was enough. If I wanted more, I could get another one. Okay? But I think 4 is good. And now I want to see what happens after 1. Okay? What's happening after 1? Well, I've got 1 point here. Let's do 1. Let's do 2. See if we can get a good point. 2, 8. So 2, 8, I think is right there. If I do 3, I think I'm going to go off my graph. No, just barely still on. 3, 9.4. So 3 up right there. So I have to go through this one, and that one. So it's going to be kind of like this. Stay close to that asymptote, but you've got to start curving because you're going to go through that other point. But you can't keep going straight with the curve because now you run into the other asymptote. So it's just going to go right along there. Like that. So there's no other way to connect those 3 points without making that kind of shape. All right, let's see how we did. Okay, I'm zoomed out a little more. But there's your section on the left. There's your middle section. And there's the section on the right. Again, my window is a little different, so if you wanted to see it more like what we did, I think if you do zoom 6, it should look hopefully pretty identical now. Yep, you're just barely seeing a little bit of the U shape because it's on the very top of my graph. And that's your sketch. Is there any question on that one? All right, so it takes a little practice to get good at them, but you start to kind of learn that these graphs are always in 3 sections, right? And you get the calculator to give you good points with the table. So I think I probably plotted 10 or 12 points to get that graph. Right? And remember, you just always have to stay close to asymptotes. Okay? As you start getting close to them, just make the line go right along the edge of the dotted line. Okay, and I think, let's see. Oh yeah, so that kind of asymptote that we had is called a slant asymptote. So that takes the place of the horizontal. None of the problems today are going to have horizontals. You'll have some in the homework that are slant, and that's definitely a good one to know for the test, a slant asymptote. And at worst case in the homework, you'll have one that's a parabola. But it's not going to get any higher degree than a parabola. Okay, questions on that one? All right, let me see. All right, so I had this one ready to go. Can anyone just tell me what kind of asymptote I would have here? I mean, I'm going to have a vertical, but besides that. Yeah. We're going to have a slant asymptote. Why?
Because it would be linearly. It would be to make the first power.
When you did the long division. Yeah, if you do out the long division, you have a degree 2 in the top, degree 1 in the bottom. That's a difference of degree 1. So that's another slant asymptote. But this one wouldn't be as bad because look at your denominator. There's only one number that makes it 0. In the last problem, there were 2. So this one is only going to have one vertical asymptote and one slant. So it's an easier problem. Does anyone want to see that one? It's up to you. Okay with it? Just to kind of give you an idea, it's going to look something like this. A vertical, a slant, and the graph is going to be in that section and that section. That's pretty much what it's going to look like. But you'd have to plot a few points and play with it to get that. That's pretty much what it would look like. Okay, so they just want us to graph this and just find a good window to graph it. So let's graph it and see what happens. What kind of asymptote would you expect here? Emily? A slant? Yeah, how come?
Because there's a difference of 1 degree.
Yeah, exactly. There's a difference of 1 degree. So if I'm having you graph this, there's probably something up with the problem. So let's graph it and see. Let's see what's going on. So 7x cubed plus 7x squared plus 2x. So there's your numerator divided by x cubed minus x plus 50. I'm going to do zoom 6 and just see what it looks like. I definitely can see a slant in there. If I set my y-max higher, let's see, I might even see it better. So there's the part on the bottom. And there it goes. I was waiting for it to start to curve, and it does right there. So your slant asymptote would be kind of like, maybe like that. So it's going to get closer and closer to it on the bottom and on the right. Is there anything in that graph that looks like something we might want to check out a little closer? Yeah?
It crosses the line.
It crosses it? You mean the green line?
Yeah, like the slant asymptote crosses.
Oh, right here?
Line. Yeah.
Yeah, that's okay, because what's going to end up happening is there's probably a vertical right there. So it's okay that it crosses it here. It just won't cross it as you head further to the right and further to the left. Pretty sure it's just going to go like this and just get closer and closer and closer and closer. So it's okay that it does cross it here, but that's a little different. We didn't have that before, but it's okay. Anything else we should check out a little closer, Chris?
Just look at how long it stays on 0, like on the x-axis.
Yeah, it looks like it kind of stays on the x-axis a while, right? Let's zoom into that and see what's going on there. So that's between like -4 and +2. So let's zoom in from -4 to +2. And let's set it from -1 to 1. Okay, so we can kind of zoom in. -1 to 1. Right, and let's see what it looks like now. Let's put that there and let's look at it now. Okay. What do you think I should do now? I'm still not 100% sure what I'm seeing here. Yeah?
Put 0 into your table. Or
I could. I mean, I could just plug in 0 and see where All right, so it has a y, it does go right through the origin, 0, 0. What might I want to do? I'm kind of starting to see something here that, because it looked pretty flat, at least in the first one. What does it look like is starting to happen now that we zoomed in? Yeah.
I feel like it goes down. It doesn't move down.
Yeah, it looks like it's maybe not staying on the axis. It might actually be going below the axis, right? So there's something here that looks kind of hidden. So let's zoom in even more. Let's go from negative 0.1 to positive 0.1. So now we're really zooming in. Just on this section right in there. Okay. So now that we've, I'll just put that there. Now that we've really zoomed in even more, we can see that that line wasn't actually straight at all. It was curved. So it actually crosses the x-axis 1, 2, 3, 4 times, where looking at the original, to me it just looked pretty flat. So the point there is if you see something that looks flat, and I ask you a question like, how many times does it cross the x-axis? Don't say, don't guess without actually zooming in a little more to check out what's going on. Because sometimes things can be hidden. So for this problem, to find a complete graph, I would say you need 2 different windows. You need a big picture so you can see the slant asymptotes and all that stuff. So the first window I had was good for that. But then to actually see what's going on here, you need a much more zoomed in window. So I think this is one of the first problems that you need 2 separate windows to really see what's going on. Okay. Any questions on that one? All right, so just make sure you zoom in and check stuff out if you need to. All right, so last question. It's a problem about rectangles, and we've done this similar kind of idea before. So this problem, I want you to think about all the different rectangles you could have with an area of 200. 200 feet by 1 foot, 10 feet by 20 feet, all the different ones. We're going to let x be the width. I want to find an equation, and then I'm going to graph it for the perimeter as a function of the width. And then once I have that equation, I want to find the dimensions of the rectangle that have the smallest perimeter. Okay, the smallest perimeter. So here I think making a picture is definitely helpful. So we've got a rectangle. And they said that I can label, what am I going to label here? They've given me something to put. The width. What did they tell me to make it? X. So let's make it X. Now, I know something else about the rectangle. What else do I know? Yep.
Area.
All right, so we should probably involve the area formula somehow. Area is length times width. The area is 200. The length, I don't know. But the width is X. So how would you write the length? You don't have to use L. We can write the length using a formula with X in it.
200 divided by x equals L.
Yeah, exactly. 200 divided by X equals L. So there's your length, there's your width. What do they want to know? A formula for the perimeter. Okay. How do you find the perimeter of that rectangle that I have right there? Yeah.
You're adding all the sides together, so you do like
Add up all the sides, yep.
2x
Yep.
plus 2 times like parentheses, yeah. 2 times 200 divided by
Yeah, and what's 2 times 200?
400.
400. So there's your perimeter. Obviously, x can't be 0, algebraically, and then geometrically it wouldn't make sense if it was 0, because if you had a rectangle with a side of 0, you don't have a rectangle. So let's graph that and see what it looks like. So 2x plus 400 over x. Now, if they said to find the rectangle with the minimum perimeter, this graph probably has a minimum somewhere. That's what I'm going to look for. Okay, I got nothing. So if we go to the table, when x is 0, we can't do it. When x is 1, I'm up at 400. When x is 2, I'm at 200. When x is 3, 4, 5, 6, 7, 8. All right, let's just go to 20. Let's go to 30. Okay, so at some point, I was going down, 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 and then between 20 and 30, I started going back up. So there's a minimum between 20 and 30 somewhere. It's way up between 60 and 73. So let's see, I'm going to go 0 to 40, and I'm going to go up to, I forgot my values. Let's go up to 200 on the y-axis. So let's go 0 to 200. So there's no wonder I couldn't see it with a standard window. I'm way off the screen. But the table kind of helped me figure it out. There we go. So here's our graph. The minimum perimeter is right in there. Specifically, I think it's right there. So let's do second calc and find what x is. Let's find the minimum perimeter. Okay, so I'm at 60. I got to go to the left first. Okay, I'm up at 70. I didn't see it go below 56, so I think the minimum is somewhere around 56. And that's when x is 14.14. X, I think, was the width. And then the length. Oh, our length was 200 divided by x. So 200 divided by 14.14. I get 14.14. So that means if you had a rectangle with an area of 200, actually doesn't matter what the area is. If you want to make a shape with the minimum perimeter, the length and width are the same. So what shape is that?
Square.
It's a square. Yep, it's a square. So we just had to find the minimum. What happens to your perimeter is x gets really, really close to 0. Yeah.
I don't think your perimeter ever changes, does it?
It does, yep. Your area never changes, but your perimeter does. What happens if x is really small, like 0.001? Your perimeter is huge, right? All of a sudden it starts to go way, way up. So now your perimeter is 400,000. So if you want to make a rectangle or make a shape and use the minimum amount of material to make the fence around it, make it a square. The more long and skinny you make it, you might have the same area inside, but you're going to use a lot more fencing to make something long and skinny versus making it a square. Okay, so that's the homework for tonight. So on page 235, 38 to 43, 45 to 47, and then 51, 52, 55, 62, and 63. Let's see. On 38 to 43, let's just, let's make it 38, and then just 41 and 43. It doesn't change it much, but. So 38, 41, and 43, so you don't have to do 42. You don't have to do 40. Okay. All right, so we'll take a look at that tomorrow.